The Goldbach conjecture is one of the oldest unsolved problems in number theory and mathematics. It was first proposed by the Prussian mathematician Christian Goldbach in a letter to Leonhard Euler in 1742. The conjecture can be divided into two related statements, the strong or binary Goldbach conjecture and the weak or ternary Goldbach conjecture. Let's explore each in detail. 1. Strong Goldbach conjecture. The strong Goldbach conjecture statement, every even integer greater than 2 can be expressed as the sum of two prime numbers. Example, 4 equals 2 plus 2, 6 equals 3 plus 3, 8 equals 3 plus 5, 10 equals 5 plus 5, etc. Historical context and origins. Goldbach initially proposed that every integer greater than 2 can be written as the sum of three primes, considering 1 as a prime number. Euler reformulated this into the modern version, every even integer greater than 2 is the sum of two primes 1. Euler's contribution. Euler found this conjecture intriguing and believed it to be true, although he couldn't prove it. His correspondence with Goldbach helped shape the conjecture into its current form. 1. Partial results and computational evidence. Computational verification. The conjecture has been verified for all even numbers up to 4 times 10 caret 18 through extensive computational efforts. 1. Statistical evidence. Heuristic and probabilistic arguments suggest that the conjecture is likely true because the density of prime numbers makes it probable that any large even number can be expressed as the sum of two primes. 1. 2. Weak Goldbach conjecture. The weak Goldbach conjecture statement, every odd integer greater than 5 can be expressed as the sum of three prime numbers. Example, 7 equals 2 plus 2 plus 3, 9 equals 2 plus 2 plus 5, 11 equals 3 plus 3 plus 5, etc. Historical context and origins. This conjecture is a direct consequence of the strong Goldbach conjecture. If every even number greater than 2 can be written as the sum of two primes, then adding another prime, 2, to an odd number greater than 5 should yield a sum of three primes 2. Proof and verification. Vinogradov's theorem. In 1937, Ivan Vinogradov proved that every sufficiently large odd integer can be expressed as the sum of three primes. This result is a significant step towards proving the weak Goldbach conjecture. 2. Helfgott's proof. In 2013, Harold Helfgott provided a proof for the weak Goldbach conjecture for all odd numbers greater than 5, completing the verification of this conjecture. 2. Significance and current status. Mathematical importance. The Goldbach conjecture is significant because it connects prime numbers, which are the building blocks of number theory, to the structure of even and odd integers. Proving or disproving it would have profound implications for our understanding of prime numbers and their distribution. 1. Current status. Despite extensive computational verification and partial results, the strong Goldbach conjecture remains unproven. It continues to be a central open problem in number theory, attracting considerable interest and research efforts. 12. The Goldbach conjecture exemplifies the beauty and challenge of mathematical problems, where simple statements can lead to deep and complex investigations. Statement of Vinogradov's theorem. Every sufficiently large odd integer can be expressed as the sum of three prime numbers. Example, for large odd integers, n, there exist prime numbers p_1, p_2, and p_3 such that n equals p_1 plus p_2 plus p_3. Historical context and proof. Historical context. Vinogradov's theorem is a weaker form of the weak Goldbach conjecture, which asserts that every odd integer greater than 5 can be written as the sum of three primes. Vinogradov's result applies to sufficiently large odd integers, providing a significant step towards proving the weak Goldbach conjecture. 1. Proof technique. Vinogradov used methods from analytic number theory, particularly the Hardy-Littlewood circle method, to prove his theorem. This method involves decomposing the problem into major and minor arcs and estimating the contributions from each part. 1. Key concepts and methods. Hardy-Littlewood circle method. This is a powerful technique in analytic number theory used to study the distribution of prime numbers. It involves integrating a generating function over a unit circle in the complex plane, separating the integral into major arcs, where the function behaves nicely, and minor arcs, where the function is more erratic. 2. Major and minor arcs. The major arcs correspond to regions where the generating function can be approximated by simpler functions, while the minor arcs require more delicate estimates. Vinogradov's proof involved showing that the contribution from the minor arcs is small enough to not affect the overall result. 2. Implications and extensions. Implications for number theory. Vinogradov's theorem provided a major breakthrough in understanding the additive properties of prime numbers. It showed that primes are sufficiently dense to ensure that large odd integers can be expressed as sums of 3 primes 1. Extensions and further research. Vinogradov's methods have been extended and refined by other mathematicians. For example, Helfgott's proof of the weak Goldbach conjecture for all odd integers greater than 5 built on Vinogradov's work and other developments in analytic number theory 2. Current status. Verification and computational evidence. While Vinogradov's theorem applies to sufficiently large odd integers, computational efforts have verified the weak Goldbach conjecture for smaller cases, providing strong evidence for its truth. 1. Ongoing research. The techniques developed by Vinogradov continue to influence research in number theory, particularly in the study of prime numbers and their additive properties. 2. Vinogradov's theorem remains a cornerstone of analytic number theory, illustrating the deep connections between prime numbers and the structure of integers. There are several significant results related to the distribution of prime numbers. 1. Prime number theorem (PNT) statement. The prime number theorem describes the asymptotic distribution of prime numbers. It states that the number of primes less than a given number, n, is approximately \frac n\log n. Mathematical formulation. If \pi n denotes the number of primes less than or equal to n, then pi n log. Implications. This theorem formalizes the intuitive idea that primes become less common as numbers get larger. 1. 2. Spashev's theorem statement. Spashev's theorem provides bounds on the distribution of prime numbers. It shows that there are constants C_1 and C_2 such that for sufficiently large nc1 log n pi n c2 log n. Implications. This result was an important precursor to the prime number theorem, providing early evidence about the density of primes. 2. 3. Bertrand's postulate statement. Bertrand's postulate, proved by Spashev, states that for any integer n1, there is always at least one prime number p such that np2n. Example, for n equals 10, there is at least one prime between 10 and 20, for example, 11, 13, 17, 19. Implications. This postulate ensures that primes are relatively evenly distributed among the integers. 2. For Riemann hypothesis statement. The Riemann hypothesis is one of the most famous unsolved problems in mathematics. It posits that all non-trivial zeros of the Riemann zeta function \zeta s have a real part equal to \frac 1, 2. Implications. If true, the Riemann hypothesis would imply very precise information about the distribution of prime numbers, refining the estimates given by the prime number theorem. 3. 5. Meyer's theorem statement. In 1985, Helmut Meyer discovered that the distribution of prime numbers exhibits certain irregularities that were not predicted by the prime number theorem. Implications. Meyer's theorem shows that the distribution of primes can have unexpected fluctuations, challenging some assumptions about their regularity. 4. 6. A twin prime conjecture statement. The twin prime conjecture asserts that there are infinitely many pairs of primes p plus 2 that are both prime. Example, 3, 5, 11, 13, 17, 19, etc. Current status. While not yet proven, significant progress has been made, including Yitung Zhang's result showing that there are infinitely many pairs of primes that differ by at most 70 million. 5. These results and conjectures form the backbone of our understanding of prime numbers and their distribution. They highlight both the regularities and the complexities inherent in the primes, driving ongoing research in number theory. Harold Helfgott's proof of the weak Goldbach conjecture is a landmark achievement in number theory. The weak Goldbach conjecture states that every odd integer greater than 5 can be expressed as the sum of 3 prime numbers. Helfgott's proof, completed in 2013, provided a comprehensive solution to this long-standing problem. Let's delve into the details. 1. Background and historical context. Weak Goldbach conjecture, proposed by Christian Goldbach in 1742, this conjecture is a simpler form of the strong Goldbach conjecture, which asserts that every even integer greater than 2 can be expressed as the sum of 2 primes. The weak version focuses on odd integers and their representation as sums of 3 primes. 1. Previous work. Before Helfgott, significant progress had been made, particularly by Ivan Vinogradov in 1937, who proved that every sufficiently large odd integer can be expressed as the sum of 3 primes. However, this did not cover all odd integers greater than 51. 2. Helfgott's approach and techniques. Major and minor arcs. Helfgott's proof builds on the Hardy-Littlewood circle method, which involves dividing the problem into major and minor arcs. These arcs represent different regions of integration over a unit circle in the complex plane. 1. Major arcs. These are regions where the generating function behaves predictably and can be approximated by simpler functions. Minor arcs, these regions require more delicate estimates due to the erratic behavior of the generating function. Improved estimates, Helfgott improved the estimates for both major and minor arcs, reducing the error term sufficiently to cover all odd integers greater than 5. This involved sophisticated techniques in analytic number theory and careful handling of error bounds. 1. 3. Key results and proof structure. Major arc estimates, Helfgott refined the estimates for the major arcs, ensuring that the contributions from these regions were accurately accounted for. This involved detailed analysis of the generating functions and their approximations. 1. Minor arc estimates, the critical part of Helfgott's proof was improving the estimates for the minor arcs. By reducing the error terms in these regions, he was able to show that the contributions from the minor arcs were small enough to not affect the overall result. 1. 4. Implications and significance. Completion of the weak Goldbach conjecture, Helfgott's proof conclusively showed that every odd integer greater than 5 can be expressed as the sum of 3 primes, thus proving the weak Goldbach conjecture. 1. Impact on number theory. This result is a major milestone in number theory, demonstrating the power of analytic techniques and the Hardy-Littlewood circle method. It also provides a deeper understanding of the distribution of prime numbers and their additive properties. 1. 5. Verification and acceptance. Peer review and publication. Helfgott's proof has been peer-reviewed and widely accepted by the mathematical community. It has been published in reputable journals and is considered a definitive solution to the weak Goldbach conjecture. 1. Computational verification. In addition to the theoretical proof, extensive computational checks have verified the conjecture for smaller cases, providing further confidence in the result. 1. Conclusion. Harold Helfgott's proof of the weak Goldbach conjecture is a testament to the depth and complexity of number theory. By refining and extending existing techniques, Helfgott was able to solve a problem that had remained open for over 270 years. His work not only resolves a significant conjecture but also advances our understanding of prime numbers and their properties. The Hardy-Littlewood circle method is a powerful and influential technique in analytic number theory, developed by G. H. Hardy and J. E. Littlewood in the early 20th century. It has been used to tackle various problems involving the distribution of prime numbers and additive number theory. 1. Overview and historical context. Origins. The circle method was developed by Hardy and Littlewood in a series of papers starting in the 1920s. It was initially applied to problems like Waring's problem, which concerns the representation of natural numbers as sums of powers. 1. Contributors. Besides Hardy and Littlewood, the method was also influenced by the work of Srinivasa Ramanujan, particularly in the context of partition functions and additive problems. 1. 2. Basic idea and structure. Generating functions. The circle method involves the use of generating functions, which are formal power series that encode information about the number of ways integers can be represented in certain forms. Example, for a sequence a(n), the generating function is g(z) equals \sum underscore n equals 0 caret \int a(n) z caret n. Integration over the unit circle. The core idea is to integrate these generating functions over the unit circle in the complex plane. This integral is then split into two parts, major arcs and minor arcs. 1. 3. Major and minor arcs. Major arcs. These are regions where the generating function can be approximated by simpler, well-understood functions. The contributions from the major arcs typically dominate and are easier to handle. Example, in the context of primes, major arcs correspond to regions where the generating function behaves predictably due to the density of primes. Minor arcs. These regions require more delicate analysis because the generating function behaves more erratically. The contributions from the minor arcs are usually smaller but need careful estimation to ensure they don't affect the overall result. 1. 4. Applications and results. Waring's problem. One of the first major successes of the circle method was in solving Waring's problem, which asks whether every natural number can be expressed as a sum of a fixed number of kth powers of natural numbers. Result. Hardy and Littlewood showed that every sufficiently large integer can be expressed as a sum of kth powers, providing an asymptotic formula for the number of such representations. 1. Goldbach conjecture. The circle method has been applied to the Goldbach conjecture, particularly in the work of Vinogradov and later Helfgott. It helps in estimating the number of ways an integer can be expressed as the sum of primes. 1. 5. Technical details and refinements. Fourier analysis. The method relies heavily on Fourier analysis, decomposing functions into their frequency components. This allows for precise estimates of the generating functions over different arcs. 1. Error terms. A significant part of the method involves controlling error terms, especially those arising from the minor arcs. This requires advanced techniques in analytic number theory. 1. 6. Modern developments. Extensions and generalizations. The circle method has been extended and refined over the years. Modern developments include applications to more complex problems in additive number theory and the study of L functions. 1. Computational advances. With the advent of computers, the circle method has also benefited from computational techniques, allowing for more extensive verification of theoretical results. 1. Conclusion. The Hardy-Littlewood circle method remains a cornerstone of analytic number theory. Its ability to tackle problems involving the distribution of primes and additive representations of integers has made it an indispensable tool for mathematicians. Statement of Waring's problem. General form. For any positive integer k, there exists a positive integer s such that every natural number can be expressed as the sum of at most s k th powers of natural numbers. Example, for k equals 2, Waring's problem asks if there is a number s such that every natural number can be written as the sum of at most s squares. 2. Historical context and origins. Lagrange's four-square theorem. Before Waring's problem, Joseph Louis Lagrange proved in 1770 that every natural number can be expressed as the sum of four squares. This result is a special case of Waring's problem for k equals 2 and s equals 4. 1. Waring's conjecture. Waring generalized this idea, conjecturing that similar results hold for cubes, fourth powers, and higher powers. He speculated specific values for s for different k, such as s equals 4, 4 squares, s equals 9, 4 cubes, and s equals 19, 4 fourth powers. 2. 3. Hilbert's theorem. Hilbert's proof. In 1909, David Hilbert proved the general form of Waring's conjecture, showing that for any k, there exists an s such that every natural number can be expressed as the sum of at most s k th powers. This result is known as the Hilbert-Waring theorem. 2. Significance. Hilbert's proof was non-constructive, meaning it did not provide explicit values for s, but confirmed the existence of such s for any k. 4. Specific values and bounds. Known values. Over the years, mathematicians have determined specific values and bounds for s for various k squares. K equals 2, s equals 4. Lagrange's four-square theorem. Cubes. K equals 3, s equals 9, proved by Wieferich in 1909. Fourth powers. K equals 4, s equals 19, proved by Hardy and Littlewood, and later refined by Balasubramanian, de Schouwers, and Dress in 1986. 2. 5. Hardy-Littlewood circle method. Application. The Hardy-Littlewood circle method has been instrumental in proving results related to Waring's problem. This method involves decomposing the generating function into major and minor arcs and estimating contributions from each part. 2. Example. Using this method, Hardy and Littlewood showed that every sufficiently large number can be expressed as the sum of a fixed number of k th powers. 6. Modern developments and computational advances. Refinements and extensions. Modern techniques and computational advances have refined the bounds for s and extended the results to larger k. For example, it has been shown that every sufficiently large number can be expressed as the sum of at most 37 fifth powers. 2. Computational verification. Extensive computational efforts have verified the conjecture for smaller cases, providing further evidence for the correctness of the theoretical results. 2. Conclusion. Waring's problem is a fundamental question in number theory that has driven significant research and development in the field. From Lagrange's four-square theorem to Hilbert's general proof and modern computational advances, the problem illustrates the deep connections between number theory and the representation of integers. The Goldbach conjecture, if proven true, would have profound implications for number theory and mathematics as a whole. Here are the key implications. Fully developed. 1. Foundational property of primes. Implication. The conjecture would affirm a fundamental property of prime numbers, showing that every even integer greater than 2 can be expressed as the sum of 2 primes. Significance. This would provide a deeper understanding of the additive properties of prime numbers, highlighting their role in constructing even integers. 1. 2. Insights into prime distribution. Implication. Proving the conjecture would offer new insights into the distribution of prime numbers. Significance. It would suggest that primes are distributed in such a way that they can always pair up to form any even number. This could lead to new theories and methods for studying prime distribution. 1. 3. Strengthening additive number theory. Implication. The conjecture would strengthen existing theories in additive number theory, which deals with the ways integers can be expressed as sums of other numbers. Significance. It would validate many heuristic and probabilistic models that predict the behavior of primes in additive contexts, providing a solid foundation for further research. 1. 4. Implications for computational number theory. Implication: a proof would have significant computational implications, as verifying the conjecture for large numbers has driven advancements in computational techniques and algorithms. Significance: these advancements could be applied to other areas of mathematics and computer science, improving our ability to handle large-scale computations and complex problems. 1. 5. Connections to other conjectures and theorems. Implication: the Goldbach conjecture is related to other important conjectures and theorems in number theory, such as the twin prime conjecture and the Riemann hypothesis. Significance: proving Goldbach's conjecture could provide insights or even partial progress towards resolving these other conjectures, as they all deal with the properties and distribution of prime numbers. 1. 6. Historical and mathematical impact. Implication: solving the Goldbach conjecture would be a monumental achievement in the history of mathematics, resolving a problem that has been open since 1742. Significance: it would demonstrate the power of modern mathematical techniques and the persistence of mathematicians over centuries. This could inspire future generations of mathematicians to tackle other long-standing open problems. 1. 7. Practical applications. Implication: while the conjecture itself is a theoretical problem, the methods developed to prove it could have practical applications in cryptography, coding theory, and other fields that rely on the properties of prime numbers. Significance: advances in understanding prime numbers can lead to more secure encryption methods and more efficient algorithms for data processing and transmission. 1. Conclusion: the Goldbach conjecture, if proven, would not only solve a centuries-old problem but also enhance our understanding of prime numbers and their properties. It would have far-reaching implications across various fields of mathematics and beyond, demonstrating the interconnectedness of mathematical concepts and the importance of prime numbers in number theory. That was all. Goodbye.